Alright, welcome back guys. We're on 12.2 day 2 now, techniques for evaluating limits still, and now we're going to do this using the graphing calculator and evaluate one-sided limits. So here we go. Alright, so first of all, limits on the graphing calculator. Sometimes it'll be obvious just visually and sometimes not, so I want to take a look at more at the not obvious ones and go from there. Okay, now I can, of course, type y equals or f of x equals this expression here into my calculator, and then to figure out the limit as x approaches 1, because again, I do have a zero denominator, so I do have an undefined sort of value, and I definitely don't have an easy factoring sort of thing or easy simplification that I can do. I might be able to rationalize my numerator, but let's just pretend, let's not do that, and let's go to the calculator here. Alright, now your table can be set up to give various things. For example, the starting value you can change. I'm going to change it to 1 for my starting value because that's the limit that I'm interested in. Okay, I don't want to start at 5 if I'm trying to figure out something about 1. Okay, another really good reason is the table step. Okay, again, that's the change as from one x value to the next that'll show up in the table over here. But, okay, now remember 1e to negative 4, okay, what this really is 0.0001. Okay, that's what I typed in, so that's 1 times 10 to the negative 4th. Alright, basically what you want to type in is some little tiny decimal. I mean, I just chose to use that one. You could have chosen any other really small decimal. But if you're counting by integers, we're not going to get a limit because, again, the limit has got to be very close to the value in question. So basically making those two changes, then go into our graph, and you can do the split screen if you have an Inspire. Alright, so here again, here's my graph. And again, if I'm interested in x equals 1, here's 1, and it's not real obvious to see what's going on, but if we go over to the table, 1 is undefined, which again is expected because I've got this 1 plugged in here would give me a 0 denominator. But you can see if I go a little tiny bit below 1 or a little tiny bit above 1, I can see 0.49987, 5.0 or 0.5, etc. So I think from there, hopefully you can make the determination that our limit, 0.49 versus 0.50, and some change, our limit here is actually equal to 0.5. And you can kind of back that up on the graph. You know, it looks like about halfway through, but so the table is a much better verification, but that's what you can do in the graphing calculator. A small table step from the value in question will at least give you a very good attempt at an approximation, and hopefully from there you can narrow it down to something that seems reasonable. Alright, moving on to one-sided limits. Okay, now sometimes we don't really care if we're going from both sides the same. We only care about either the left or right, and that's basically what a one-sided limit is. So just the left side or the right side instead of both. Okay, so here we go. Now if I have limit as x approaches 0 of 4 over x, well, here's the graph of y equals 4 over x. And okay, we can clearly see if we're approaching 0, here's my value of 0. Well, definitely on one side of it I'm going to positive infinity, on the other side of it I'm going to negative infinity. So this we would simply say does not exist. And again, if you want to abbreviate it like that, that's great. Okay, now this little plus sign right there is basically the limit from the right. Alright, so basically what that means for us is I want to go a little bit right of the value in question. Again, the value in question is still 0. I want to go a little bit to the right of 0 and then start tracing my graph back towards 0. And as I do this, notice just from the right side, hey, where is he going? Well, he's going to infinity. So my limit from the right, well, is infinity. Alright, same basic idea over here, although with the minus sign, well, hopefully it's pretty obvious based on what I just did, is that means I want the limit from the left. Okay, so same basic idea, again, just going to the left. I want to go to the left of my value in question, which is 0, kind of pick a point and then just start tracing my graph. And as I do that, notice I'm kind of falling off the table here, so my limit from the left for this particular expression would then be negative infinity. Alright, so if you're only worried about the left or the right side, yeah, ignore the other side and go with it. If I give you a limit and don't specify one side or the other, I need to match both sides. Otherwise it doesn't exist. But if I only say one side or the other, you can just go with whatever that side is going towards. Hopefully that made a little sense. Alright, so let's throw a tricky one at you here. Okay, now the limit as x approaches pi from the right of x times cotangent x. Alright, so here's our graph again. This is radians in case it's not obvious. Hopefully the pi is a dead giveaway as radians. But anyway, the graph I have admittedly is not the greatest for this because it's not in terms of pi, it's whole numbers here. But, okay, hopefully knowing enough about cotangent and the asymptotes that show up, right here, this is my value for pi. Okay, so that's an asymptote right there, not actually part of the graph. Okay, so again, there's where pi is, and I want to approach pi from the right. So again, here's where I am. I want to go a little bit to the right, and let's change colors just because we can. And again, I get a little bit to the right, and then I start tracking my graph. And what's my graph doing? Well, hey, it's shooting up straight to infinity, so that's what my limit is from the right-hand side. Again, if I didn't have that little plus sign on there, I'd have to say does not exist, because on the left it's going down, and on the right it's going up. Since I only specified the right side, I can say my limit is infinity. Alright, now the book makes a big deal of it, and I'll do it just momentarily at least. Using one-side limits to find limits. Okay, so basically here this is kind of almost geometry theorem sounding to me, but here it is. Alright, if the limit as x approaches a from the right of the function equals the limit as x approaches a from the left of the function equals some value b, then the limit, two-sided version, as x approaches a of the function is equal to that same b. Okay, now what I've got over here in green is basically the English translation of that. And that's if the limit from the right equals the limit from the left, the two-sided limit is that number. Alright, so basically it's just comparing the left side and the right side and saying, okay, hey, they match, then I got my answer here, or if they don't match, of course, then Catty Heron shows up again, and we say the limit does not exist. But here we go. Alright, so here we go. We've got the limit as x approaches -4 of the absolute value of x plus 4 over x plus 4, and it gives us this graph here. Okay. Okay, maybe not obvious since there's so many tick marks here on this particular program I decided to use, which is an emulator for the Inspire. But right there is my -4 value. So that's where the jump occurs, if you will. Okay, so basically here, what we can do is say the limit as x approaches -4 from the left of the original function, I'll just write f of x instead of recopying that whole thing, equals, it looks to be about a -1. And then the limit as x approaches -4 from the right of our function, well, if I'm going from the right, I'm up here, so I'm over at +1. Okay, therefore, the limit as x approaches -4 from both sides of the function does not exist. Okay, again, if these two numbers were the same, we would say that number, whatever that number happened to be. Since those were different, we say it does not exist. Alright, now admittedly that last one was a does not exist case, so let's take a look at one that maybe it actually exists. Alright, so again, same thing, but this is kind of just a formalized version of what hopefully you've done previously on some of these problems. Alright, so anyway, limit as x approaches 3 of f of x. Okay, and again, maybe not real clear, but there's my 3. And looking up here, at least visually, it looks like it matches up. Alright, so, but you know, things can be deceiving. Maybe it's off by a very small decimal or something like that, so we do have to go through some steps here and make sure we got what's going on. Here we go. So the limit as x approaches 3 from the left of the original f of x equals, okay, now here admittedly it looks this way, it looks like it matches, and actually if you went through the table in your calculator you could do this, but I want to just demonstrate this algebraically for the sake of being able to do it, or at least showing you another option here. Alright, so if I want to approach 3 from the left, okay, well if I'm approaching 3 from the left, I'm on the parabola part of the graph. And as I do that, okay, if I want to algebraically test this, well I sure better plug that value into the parabola, half of the graph. So I'm plugging my 3 into this, so I get 3 squared plus 2 times 3 minus 8. And again, just ballparking this thing, it looks we're somewhere around 7, maybe 8, something like that. Alright, so 3 squared is 9. Plus 2 times 3 is 6, minus 8, that's 15 minus 8, and that equals 7. Okay, cool. So the limit from the left side is 7. But, does that match the right side? Well, let's check it out. Limit as x approaches 3 from the right of our function. Okay, let's change colors. Okay, now if I'm coming in from the right, that means I'm coming down this linear part. And so again, just to verify it, I want to make sure I plug into the linear part now. And so that's going to be 2 times 3 plus 1. Hopefully that one's not too much of a challenge. We can get a 7 right there. And then, hey, look at that. These two guys match, so we're just happy all over the place. Okay, so again, as what we can say from there is that the limit as x approaches 3 from both sides of that original function is 7. Okay, again, just that idea that, hey, if it's the same on both sides, it matches. So again, book makes a big deal of it a little bit, but you know, I just think it's kind of what we've been doing so far, just made into fancy notation and stuff like that. But there it is. Hopefully that made a little bit of sense. Alright, I didn't squeeze it anywhere else in the presentation, so here's the assignment. As always, anything you're not sure about, ask me for help in class. For instance, if you have trouble typing the piecewise function into your calculator, sometimes that can be tricky. Ask me in class, I can help you on either model calculator that you may have. Alright, see you then.